All right, I am going to work through a derivation for this special relativity gamma correction factor. It's an interesting proof. We have to use our imagination a little bit. The math actually is surprisingly easy. It's just some substitutions and Pythagorean theorem, really. Um, the weirdness is the setup and basically Einstein's idea that time is different depending on your state of motion. Einstein built special relativity off of the idea that the speed of light is constant. That's the only thing we can count on to be constant. So our proof for this gamma constant is founded on its fundamental piece is that we're always going to assume that the speed of light is constant. We're going to tackle this by thinking about time, and we're going to tackle it by thinking about time using a special clock that uses light, since we know that the speed of light is constant. So this little diagram I stole off the internet. This is our new version of a clock. Down here at the bottom there's a source of light, so imagine a little laser beam. It's going to send a pulse of light upward. The pulse of light travels upward. I'm going to call this a distance of h for height. It hits a mirror at the top, and then that pulse of light reflects back downward, and it hits a detector. Based off the hardware of this knowing when the laser pulse was sent and when the laser light was received, we can use this as sort of a clock. Every tick is how long it takes for the laser pulse to go up and back down. We know that speed is distance over time. Distance over time. And we know we're talking about light, so the speed of light is our speed. It travels h all the way up and h all the way down, and so it travels at 2h in a time of t. So our clock, the time it takes for that pulse to happen, we can rearrange this and say that that time is equal to 2h over c. We're going to use that later. Because I know it's coming later, this will make sense later in the proof, but I'm going to take that and I'm going to square that just to make later a little bit easier. If I square it, I get t squared equals 4h squared over c squared. We'll need that later. So this is my light clock. It just shoots a pulse of laser up, hits a mirror, bounces back down. Because the speed of light is constant, that's going to zip back and forth. The light's going to move at a constant speed of c. If I'm standing right beside this thing, I don't see it as moving. From that frame of reference, I could say that the t is 2h over c, and if I square it, I get that 4h squared over c squared thing that we'll need later. Special relativity is all about moving. So if that's what the clock looks like to me standing right beside it, what if we took that clock and put it in a train or a car or an airplane? Einstein always thought about trains back because that was sort of the mode of transportation when he was around in the late 1800s. What if we put that whole thing in a train and it was moving sideways? So the follow-up picture, here's my same apparatus. Now it's moving sideways at some speed v. The light still leaves the laser source, bounces off a mirror, and gets back to the detector. But because it's moving, I can't assume that the time it takes is exactly the same. If this thing is, I'm gonna build a triangle. We know that this height hasn't changed. We're gonna call that h for height, just like I called it before. It's gonna move sideways some sort of distance. I'm gonna make a triangle, so I'm gonna chop it there. If it's moving at speed v, it moves at v for some time. What I can't do is assume that the time it moves for is the same as the time up in this situation. In this situation, it took a certain amount of time for the laser beam to get up and down, but in the second situation, because we're observing something that's moving, the time may be different. So we're going to call it a different letter t. If that's the case, then this whole side of the triangle, it moves sideways at some speed v for time t. This distance would be v multiplied by t. Distance is always speed multiplied by time. That means when I'm setting up my triangle that this shorter distance, it's halfway there. So this is going to be v times t all over 2. I'm curious about this side of the triangle. So kind of messy, but here's what I got. A sideways motion, it moves sideways a distance of v times t all over 2. I defined the height of our clock as h, and I'm curious about side. I called it capital D. From Pythagorean theorem, d squared is h squared plus v times t all over 2 squared, or d squared equals h squared plus 1/4 v squared t squared. If I'm standing outside of this looking at this light clock, I'm expecting that the t I'm going to get here is going to be a bigger t than what we got up here. When I look at something that's moving, everything's in slow motion, so I'm going to tick through more seconds than the person inside the train ticks through. So I'm expecting capital T to eventually be larger than lowercase t. Lowercase t, it wasn't moving through space, so they're clicking through time as quickly as possible. But if I change perspective, if I look at that clock from standing outside this moving train, as Einstein would picture it, since it is moving, since it's moving through space, it has to tick through less time. So I'm expecting capital T, the time I measure outside of the train, to be bigger because little t has ticked through fewer seconds since it's ticking faster. Hopefully that makes sense. Pythagorean theorem leads me to what d is, but also d is the path that the light followed. We know that speed is distance over time. Capital D is what the light actually did. So the light moved at a speed of c. The time it took, if it took capital T for that whole thing to happen, then the time it took for the light to go just one length, one of those hypotenuses, would take half the time. So from speed equals d over t, I know that the speed of light is d over t over 2. Or if I flip it around, d must be c times t all over 2. Just flip the t over 2 to the other side. Now I can combine these two things. From Pythagorean theorem, d squared was equal to that mess. So if I take ct over 2 and square it, that's got to be equal to the Pythagorean theorem thing. Squaring it, the 1 over 2 squared gives me 1/4 ct, oops, that should be a lowercase c, so just emphasize that. C for the speed of light, t squared equals h squared plus 1/4 v squared t squared. Nobody likes fractions, so I'm going to multiply the whole thing by 4 to get rid of that fraction of 4. So I get c t squared equals 4 h squared plus v squared t squared. The whole point of this is I'm curious about t squared. So let's try and get t squareds kind of together. So if I bring it over, I can get, oops, I goofed in here. The c squared should have been, sorry, backtrack. When I expanded out and squared the c over t all 2, I got the 1/4, and I forgot to put a square by the c. So hopefully that doesn't, well, now it's good. What I've got there is good. I want to combine the t's. I'm curious about capital T, so I'm going to bring the other t squared over. It's a subtraction. And that's equal to 4h squared. If I common factor out the t squared, I'm left with c squared minus v squared equals 4h squared. To go farther, I'm going to divide, and this is kind of because I know what's coming up, I'm going to divide both sides by c squared. I'll tell you why I'm doing that in a sec. If I divide everything by c squared, on the left, I've got t squared equals 1 minus v squared over c squared. That should start to look familiar. And on the right, I've got 4h squared over c squared. The reason I divided by c squared was, if we think back, if we look back, this is the one I starred. 4h squared over t squared is exactly what the time for the other observer sees. It's the other t squared. So in my proof, if I go back here, 4h squared over t squared is t squared. So I can say t squared multiplied by 1 minus v squared over c squared is exactly the same as the other time squared. I'm curious about capital T, so t squared equals, divide both sides by that mess, 1 over 1 minus v squared over c squared. I didn't really need brackets, and I had a t squared on the numerator. To get t all by itself, square root both sides, I get t equals the square root of 1 is 1. On the denominator, I've got the square root of 1 minus v squared over c squared, all multiplied by t. That's how we get the gamma. Oops. This is the gamma that we're used to. So we could say t is equal to gamma multiplied by t, where gamma is equal to 1 over square root of 1 minus v squared over c squared. If we stood still on the train, time would tick really fast for us, and we tick through a certain amount of seconds. If we stood outside the train, we would be experiencing delta t. If we look at that other clock, we would tick through however many seconds they tick through multiplied by gamma. Gamma is always the number bigger than 1. Let's say it's going so crazy fast that gamma equals 2. Someone inside the train would see time tick by and see so many seconds go by on their watch. Someone standing outside the train would see twice as many seconds tick by. So if you were standing outside on the train, maybe 4 seconds went by on your watch. Inside the train, whoever watched that ticking laser tick up and down, only 2 seconds went by on their watch. So this little proof, this little derivation comes up with a gamma that shows you how time is dilated. I'm not going to do the proof for it, but there's some reasoning for why it's the same factor for length and mass. If you're curious, let me know and I can Google show you a cool proof online, or see if you can find it on your own.